You're wearing it right now. That soft fabric against your skin, the shirt you pulled on without a second thought this morning. But have you ever stopped to wonder where it truly began? Not in a store, not even in a sewing room, but in a sprawling field under the burning sun, where white clouds bloom from green plants, and inside industrial fortresses where cotton undergoes one of the most fascinating transformations in modern manufacturing. This is the hidden journey your t-shirt took before it ever touched your body. Welcome to the world of cotton harvesting and textile manufacturing, a realm few people ever witness, where nature meets cutting-edge technology in spectacular fashion. What you're about to discover will change the way you look at every piece of clothing in your closet. Because behind that simple t-shirt lies an extraordinary process involving machines that can pick cotton faster than 200 human hands, factories that process fiber with surgical precision, and engineering marvels that transform a fluffy plant into the second skin you wear every single day. The cotton plant holds secrets that have shaped human civilization for over 7,000 years, yet the modern process of turning it into your favorite shirt remains virtually unknown to most people. Inside the facilities you're about to explore, cotton undergoes metamorphosis through stages so precisely controlled that a single degree of temperature variation could ruin an entire batch. The machines you'll encounter cost millions of dollars and operate with tolerances measured in thousandths of an inch. This isn't just about picking a plant. This is about the convergence of agriculture, chemistry, physics, and industrial artistry. From the moment those cotton bolls open in the field to the instant that finished fabric rolls off production lines, you're witnessing a manufacturing ballet performed at scales that defy imagination. Factories process tons of raw cotton every single hour, transforming it through processes that would seem like magic to anyone from just a century ago. And it all starts in places most people will never see, with techniques most will never understand. Prepare to step inside the forbidden world of cotton harvesting and t-shirt manufacturing, where industrial secrets become visible and the ordinary becomes extraordinary. Let's begin with something that will immediately change your perspective on cotton. Each cotton boll, those fluffy white clouds you might picture in a field, contains approximately 1,500 individual fibers. When you touch a typical t-shirt, you're actually touching fibers from roughly 3,000 to 4,000 different cotton bolls. That single garment represents the combined output of multiple cotton plants, harvested, processed, spun, and woven through processes involving hundreds of individual steps. But here's what makes cotton truly remarkable from an engineering standpoint. Cotton fiber is almost pure cellulose, one of the strongest natural materials on Earth when you consider its weight-to-strength ratio. Under a microscope, each cotton fiber looks like a twisted ribbon, and this natural spiral structure is what gives cotton its incredible ability to trap air, making it breathable and comfortable. The twist in cotton fiber isn't random. It occurs as the fiber dries after the boll opens, creating a spring-like structure that gives cotton fabric its resilience and flexibility. Modern cotton harvesting machines can pick cotton from 8 rows simultaneously, traveling at speeds up to 5 miles per hour, harvesting as much cotton in 1 hour as 20 people could pick by hand in an entire day. These mechanical monsters, called cotton pickers, use rotating spindles covered with barbed teeth that grab the cotton while leaving the plant intact. The engineering behind these machines represents decades of agricultural innovation, with some models featuring GPS guidance systems accurate to within 2 centimeters, ensuring not a single plant is missed. The United States, China, and India together produce over 60% of the world's cotton, with the US state of Texas alone harvesting more cotton annually than most countries on Earth. American cotton farms average around 1,000 pounds of cotton per acre, but the most advanced operations using precision agriculture techniques can achieve yields exceeding 1,400 pounds per acre. This dramatic increase comes from satellite-guided planting, drone-based monitoring, and data analytics that optimize everything from irrigation to harvest timing. Here's something that will blow your mind about cotton quality. Not all cotton is created equal. The industry grades cotton based on fiber length, with the longest fibers called extra-long staple cotton measuring over 1.38 inches. Egyptian cotton and Pima cotton fall into this category, and these premium fibers make up less than 3% of global cotton production. The vast majority of cotton is upland variety, with fiber lengths around 1 inch. Why does this matter? Longer fibers create stronger, smoother yarns that produce softer, more durable fabrics. The difference you feel between a cheap t-shirt and a premium one often comes down to those fractions of an inch in fiber length. The cotton plant itself is an evolutionary marvel. It's one of the few crops where humans harvest the seed pod coating rather than the seed itself. Those fluffy white fibers evolved to help cotton seeds disperse on the wind, traveling miles from the parent plant. Humans have simply hijacked this natural dispersal mechanism for textile production. Wild cotton still exists in tropical regions, but modern commercial cotton has been selectively bred for thousands of years to produce longer, stronger, more abundant fibers. Temperature plays a crucial role in cotton cultivation that most people never consider. Cotton plants require at least 200 frost-free days to mature properly. They need hot weather during growth but actually produce better fiber quality when temperatures drop slightly during boll development. This is why premium cotton regions have specific climate profiles: hot summers but cooler nights during the harvest season. The temperature differential between day and night actually strengthens the fiber structure, creating cotton with superior textile properties. Cotton harvesting timing is so critical that farmers use sophisticated instruments to measure moisture content in the bolls before beginning harvest. If cotton is picked too wet, it will rot in storage. Too dry, and the fibers become brittle and break during processing. The ideal moisture content for harvesting is between 6 and 12%, and farmers monitor their fields constantly, sometimes waiting for specific weather windows that might last only a few days. Make sure you hit that subscribe button and like this video, because what you're about to learn next gets even more fascinating as we step inside the processing facility where transformation truly begins. The relationship between cotton and human civilization runs deeper than most realize. Archaeological evidence shows humans were weaving cotton fabric in the Indus Valley over 5,000 years ago. Cotton textiles found in Mexican caves date back to over 7,000 years. This plant has clothed humanity longer than recorded history, and the basic process of turning cotton fiber into thread hasn't changed conceptually, even though the technology has evolved beyond recognition. Modern cotton breeding programs use advanced genetics to create varieties resistant to specific pests, tolerant of drought conditions, and optimized for mechanical harvesting. Some cotton varieties are now designed to open their bolls uniformly, with all bolls on a plant reaching harvest maturity within a narrow window. This uniformity allows for more efficient machine harvesting and reduces the number of passes through the field. Scientists have even developed naturally colored cotton varieties that produce fibers in shades of brown, green, and even pink, though these remain specialty products with limited commercial production. The environmental footprint of cotton production has become a major focus in recent years. Conventional cotton requires significant water and pesticide inputs, but innovative farming techniques are changing this. Precision agriculture uses sensors and data analytics to apply water and nutrients only where needed, reducing waste dramatically. Some advanced farms now use less than half the water per pound of cotton compared to traditional methods. Integrated pest management reduces chemical pesticide use by introducing beneficial insects and using pheromone traps to monitor pest populations. Cotton fiber has unique chemical properties that make it ideal for textile production. The fiber is almost pure cellulose, arranged in a structure that gives it exceptional moisture absorption. Cotton can absorb up to 27 times its own weight in water, which is why cotton towels work so effectively. The fiber's cellular structure features a hollow core called the lumen, surrounded by concentric layers of cellulose. This hollow structure contributes to cotton's excellent insulation properties and its ability to dry relatively quickly despite absorbing so much moisture. When cotton bolls open in the field, the fluffy white fiber you see is actually already mature, complete fiber. Unlike wool that grows continuously or synthetic fibers that are extruded, cotton fiber reaches its final length and thickness while still attached to the seed. The fiber stops growing once the boll opens, and exposure to air causes it to dry and twist into that characteristic ribbon shape. This natural maturation process means cotton quality is determined largely by growing conditions before harvest, not by processing afterward. The global cotton industry supports over 250 million people worldwide, from farmers to factory workers to textile designers. Cotton-growing regions support entire economies, with some communities depending almost entirely on cotton for their livelihood. The crop has shaped political history, geography, and trade patterns for centuries. The American South's economy was built on cotton. India's independence movement involved boycotts of British cotton textiles. The cotton belt across southern United States got its name from the crop that defined the region. Raw cotton straight from the field looks quite different from what most people imagine. It's not purely white. It's often cream-colored, sometimes with pink or brown tints depending on variety and soil conditions. The pristine white cotton most people picture comes after cleaning and sometimes bleaching. Raw cotton also contains pieces of leaf, small twigs, dirt, and most importantly, the cotton seeds themselves. These seeds make up roughly 2/3 of the weight of raw cotton as it comes from the field. Separating fiber from seed is one of the first critical steps in cotton processing. Cotton's breathability comes from both the fiber's hollow structure and the spaces between fibers in woven or knitted fabric. Air can flow through these spaces, allowing heat and moisture to escape from the skin. This is why cotton remains the preferred fabric for hot weather clothing. Synthetic fabrics can be made to wick moisture, but they generally don't match cotton's combination of moisture absorption, air permeability, and comfort against skin. The fiber's natural properties simply can't be perfectly replicated with artificial materials. The cotton harvesting season creates dramatic activity in cotton-growing regions. During peak harvest, cotton gins and processing facilities operate 24 hours a day, 7 days a week. Trucks loaded with fluffy cotton form long lines at gin facilities, waiting to unload. The urgency comes from weather. Once cotton bolls open, they're vulnerable to rain, which can stain the fiber and reduce quality. Farmers race against weather forecasts, trying to harvest their entire crop during fair weather windows. A single rainstorm can cost a cotton farmer thousands of dollars in reduced fiber quality. Raw cotton begins its transformation the moment it leaves the field. Harvesting machines deposit cotton into large module builders, creating compact rectangular blocks weighing up to 13 tons. These modules, wrapped in protective covering, can sit in the field for weeks if necessary, waiting for transport to processing facilities. The module system revolutionized cotton logistics, allowing farmers to harvest quickly when weather conditions are optimal without being constrained by immediate processing capacity. Transport trucks fitted with special module handling equipment pick up these massive cotton blocks and deliver them to cotton gins. A gin facility is where cotton undergoes its first major industrial transformation. The building itself is typically a sprawling industrial complex with massive storage barns, processing equipment that towers several stories high, and baling operations that compress processed cotton into dense packages for shipping. The ginning process begins with feeding systems that break apart the modules and transport cotton through the facility. Powerful fans and conveyor systems move the fluffy fiber, which at this stage is still mixed with seeds, leaves, stems, and field debris. The cotton passes through cleaning equipment that removes the largest pieces of trash through a combination of mechanical beating and airflow separation. Heavier debris falls away while the lighter cotton continues through the system. The heart of the gin is the saw gin system, invented over 2 centuries ago but refined to remarkable efficiency. Rotating cylinders covered with thousands of circular saw blades grab cotton fibers and pull them through narrow slots. The slots are too small for cotton seeds to pass through, so the fibers separate from seeds at this point. The seeds fall into collection systems, while the now seed-free cotton fiber continues to processing. Modern gin systems can process over 15 tons of seed cotton per hour, separating roughly 5 tons of usable fiber. After ginning, cotton passes through additional cleaning stages. Stick machines remove any remaining plant material. Lint cleaners use fine-toothed cylinders and air jets to extract the tiniest particles of debris. Each cleaning stage removes impurities but also risks damaging fibers, so engineers constantly balance cleanliness against fiber quality. Overcleaning can shorten fiber length and reduce cotton value. Undercleaning leaves impurities that cause problems during spinning. The cleaned cotton then moves to the baling press. where hydraulic systems compress it into dense rectangular bales. A standard American cotton bale weighs approximately 500 pounds and measures roughly 33 inches wide by 54 inches long. The bale press compresses cotton to about 1/10 its original loose volume, making it economical to transport and store. Workers wrap finished bales in protective covering and tag them with information about cotton variety, quality grade, and origin. Cotton classification happens at this stage. Trained classifiers or sophisticated optical instruments analyze fiber length, strength, color, and purity. This grading system determines cotton value and directs it to appropriate manufacturing applications. The highest grades command premium prices and go to manufacturers producing luxury textiles. Lower grades suit industrial applications or products where fiber quality matters less. The classification system is so refined that it recognizes over 30 distinct quality levels. From the gin, cotton bales travel to textile mills, facilities that specialize in transforming raw fiber into fabric. A modern spinning mill is an engineering marvel, containing equipment that costs tens of millions of dollars and occupies factory floors the size of multiple football fields. The air inside is carefully controlled for temperature and humidity, because cotton fiber properties change with atmospheric conditions. Most mills maintain relative humidity between 65 and 70%, keeping fibers pliable and reducing static electricity. The spinning process begins with opening and blending. Workers feed cotton bales into opening machines that tear the compressed fiber back into loose form. Multiple bales from different origins are often blended at this stage to ensure consistency. If one bale has slightly longer fibers and another has stronger but shorter fibers, blending creates a homogeneous mix with balanced properties. The opened cotton looks like a thick cloud, moving through the factory on conveyors. Carding machines perform the next transformation. These devices contain thousands of fine wire teeth on rotating cylinders. As cotton passes through, the teeth separate individual fibers, remove any remaining impurities, and begin aligning fibers parallel to each other. The carding machine output is a thin web of fiber that gets condensed into a soft, rope-like form called a sliver. This sliver, pronounced sliver, is the first stage where cotton starts resembling something that could eventually become thread. Drawing frames take multiple slivers and combine them while stretching the combined strand. This process further aligns fibers and improves uniformity. The output is still a sliver, but with better fiber orientation and more consistent thickness. Some mills run cotton through drawing frames multiple times, progressively improving quality. Each passage through the drawing frame makes the final yarn stronger and more uniform. Roving frames perform additional stretching and insert a slight twist. The roving process reduces the strand diameter while adding just enough twist to hold fibers together during the final spinning operation. Roving winds onto bobbins as a soft, twisted strand roughly the diameter of a pencil. These roving bobbins feed the spinning frames where cotton finally becomes true yarn. O-ring spinning, the most common yarn production method, uses spindles rotating at extraordinary speeds, sometimes exceeding 15,000 revolutions per minute. The roving feeds onto the spindle while rotating, inserting twist that locks fibers together. Simultaneously, the strand is stretched thinner. The amount of twist and the degree of stretching determine final yarn properties. More twist creates stronger yarn but reduces softness. Less twist produces softer yarn with less strength. Engineers calculate precise twist levels for each yarn application. Modern mills also use alternative spinning technologies. Rotor spinning, also called open-end spinning, produces yarn without traditional spindles, achieving even higher production speeds. Air-jet spinning uses compressed air vortices to insert twist. Each technology has advantages for specific yarn types and applications. For basic t-shirt fabric, ring-spun yarn remains the standard due to its balance of strength, softness, and cost. The yarn coming off spinning frames winds onto cones or tubes, ready for knitting or weaving. Most t-shirt fabric uses knitted construction rather than weaving. Knitting creates a fabric structure more elastic and comfortable than woven textiles. Circular knitting machines, the type used for t-shirt material, contain dozens or even hundreds of needles arranged in a circle. Yarn feeds into these needles, which interloop the yarn to create tubular fabric. A single circular knitting machine can produce fabric at remarkable speeds, sometimes creating several hundred pounds of knitted material in a single day. The fabric emerges as a continuous tube, wound onto large rolls for subsequent processing. At this stage, the fabric is called greige goods, pronounced grey goods, even though it might be off-white or cream-colored. Greige fabric contains natural oils, waxes, and impurities that must be removed before the fabric is suitable for clothing. Fabric preparation involves several chemical treatments. Singeing passes fabric quickly over gas flames, burning off loose surface fibers that would otherwise create a fuzzy appearance. Desizing removes starches and sizing agents used during yarn production. Scouring uses detergents and heat to remove natural waxes, oils, and dirt. These cleaning processes happen in large industrial machines where fabric passes through multiple chemical baths at controlled temperatures. Bleaching makes fabric white if that's the desired final color. Most cotton fabric destined for white t-shirts goes through bleaching using hydrogen peroxide under alkaline conditions. The process removes natural cotton pigments without damaging fiber structure. Careful control is essential because excessive bleaching weakens fibers and creates harsh, brittle fabric. After bleaching, fabric goes through thorough washing to remove all chemical residues. Dyeing follows if the t-shirt will be colored. Industrial dyeing equipment comes in various designs, but jet dyeing machines are common for knitted fabric. These machines circulate fabric through dye baths at high speeds, ensuring even color penetration. Temperature, time, chemical auxiliaries, and dye concentration all affect final color. Achieving consistent, repeatable colors requires precise control and sophisticated quality monitoring. Some colors are notoriously difficult to dye consistently. Navy blue and black, for example, require careful process management to avoid shade variations between production batches. Finishing treatments give fabric its final properties. Mechanical finishing might include brushing to create a softer surface texture or compacting to reduce shrinkage. Chemical finishes can add properties like wrinkle resistance, though such treatments are less common for basic t-shirts. Most t-shirt fabric receives minimal finishing to maintain cotton's natural feel and breathability. The finished fabric travels to cutting and sewing facilities. These might be part of the same manufacturing complex or separate operations. Modern cutting uses computer-controlled systems that optimize pattern layout, minimizing fabric waste. Automated spreaders lay out multiple layers of fabric, sometimes 100 layers thick. Cutting machines then slice through all layers simultaneously, following patterns calculated for maximum efficiency. Sewing t-shirts involve specialized machines designed for knitted fabric. Overlock seams, created by serger machines, are common in t-shirt construction. These seams are stretchy, preventing seam breakage when the fabric stretches. Collar and sleeve attachment requires precise alignment. Industrial sewing machines operate at speeds unthinkable on home machines, sometimes creating several thousand stitches per minute. Quality control inspectors check garments at multiple points during production. They verify seam strength, check for fabric defects, ensure proper sizing, and confirm that garments meet specifications. Rejected items get analyzed to identify whether problems originated in fabric production, cutting, or sewing. This feedback loop helps manufacturers continuously improve processes and reduce defect rates. Finished t-shirts go through final inspections, folding, and packaging. Some facilities use automated folding equipment that produces perfectly uniform results. Others employ skilled workers who fold each garment by hand. Packaging might be as simple as plastic bags or as complex as custom boxes with tissue paper and branding materials, depending on market positioning and price point. From cotton ball to finished t-shirt, the journey involves hundreds of individual processing steps, dozens of machines, and the coordinated efforts of agricultural workers, factory operators, machine technicians, quality inspectors, and countless other professionals. The entire supply chain, from planting cotton seeds to delivering finished garments to stores, can take 6 months or longer. Yet the result is something so commonplace, so ordinary, that most people never consider the extraordinary complexity behind it. So now you understand what really happens between the cotton field and your closet. But the world of textile manufacturing holds even more secrets. Have you ever wondered about the most luxurious fabric in the world, cashmere? The process behind creating cashmere is even more remarkable than cotton, involving rare animals in some of the world's most remote locations, and manufacturing techniques so specialized that only a handful of facilities globally have mastered them. That video just appeared on your screen, and trust me, what you'll discover will absolutely blow your mind. Before you go, drop a comment below and tell me, what surprised you most about how t-shirts are made? Was it the mechanical cotton pickers, the speed of industrial spinning, or something else entirely? I read every comment, and your feedback helps me create better content. And if you enjoyed uncovering the hidden world behind everyday products, hit that subscribe button and ring the notification bell. There's so much more to explore, from the factories that make your favorite foods to the industrial processes behind the technology you use every day. Trust me, once you start seeing the world through this lens, you'll never look at ordinary objects the same way again. See you in the next video, where we are going deep into the secret world of luxury.